Welcome everybody to this video that presents the results coming from a project entitled Toward Net Zero Infrastructure, Advancing the Environmental Economic Appraisal of Power Plants. This project and especially this video will be focused on one single case, the case of nuclear power plants to mitigate the risk of droughts. So this project and also this video is part of a broader and bigger project towards net zero infrastructure, advancing environmental and economic appraisal for power plants funded by the Italian government through PRIN 2022. And we acknowledge and thanks for these opportunities and the funding received. This project has been developed together between colleagues from Politecnico di Milano and colleagues from the Università degli Studi di Brescia. It has been a team effort, so there is myself, Alessandro Paravano, as well as colleagues Professor Alessandra Neri, Professor Giorgio Locatelli, and Professor Enrico Cagni. Before starting, let me do a very quick and short disclaimers on the criteria that we use to select the cases. So, given the nature of the research, which aims to produce basic research funded by public funds, and the results intended to be disseminated and made accessible to the public, we decided to select cases that are based on accessible public data. So these cases have been selected for their convenience in illustrating the different methodologies potential that represents and do not represent a judgment of merit on the technology itself. Also, part of the research and the selection criteria has been supported by the good knowledge that Professor Locatelli has in this domain. And we also want to thank Giacomo Galeotti, who was a master student. He developed part of the data collection analysis of this work, supervised by Professor Giorgio Locatelli and me, and we acknowledge and sincerely thank him for his contribution. So let me start with the case study on this nuclear power plant. So as we have already discussed it also in another video, the idea of this project is to overcome some barriers that we have in assessing the uncertainty and the return of investment in terms of CO2 of complex infrastructure, especially energy power plants. So we selected a plausible and relevant case study to model and assess the effectiveness of this new approach that we have developed. So the key case and the key risk, we really intend to address the mitigation of drought risk through the life cycle of a nuclear power plant. The idea is to contribute both in practical and methodological way and to illustrate the methodologies through this case. So let me start from the beginning. So as we know, climate change is changing, and one of the key phenomena where increasing witnesses is shown in the graph below. So on the x-axis, you can see the years and numbers of drought events globally, and this phenomenon is extremely relevant, particularly in Italy and Europe. And just to give you a sense of the scale, in France, 2022, a severe drought forced EDF to reduce output in several nuclear power plants, with production dropping to as low as 40% of their maximum capacity. It was mainly due to the lack of water availability to properly cool the reactors. So the key assumption of our work is that a reduction in the energy production beyond having economics per action which are not the focus of this project and this exercise, also has a strong impact on greenhouse gas emissions, GHG, that energy will be replaced because the energy will be replaced by non-green sources. And so how can we mitigate a better modeling this kind of risk? So we decided to develop a project, a research that is based on real option modeling and we select as the option to mitigate the risk, and that is something that we're going to evaluate, building a backup water reservoir that the plant can draw from in case of drought. So the key question is it worth doing it? If so, when? And also, how large should be this basin be? And considering also, and we are fully aware that exercising this option entires CO2 emission both for building and operating the basin. Indeed, in terms of operation, we assume that there will be some pumps transferring water to the reactors. To develop the model, we focus on a case, the Caorso case. It was the largest and most recent operational nuclear plant in Italy before the national nuclear power program was shut down, and it's real. A lot of accessible data are available for this context, and this power plant is also located in an area with significant variability in the flow of the Po River, which has been increasingly suffering from drought in recent years. As per the plant type, you can see here the key figures. So up here, 1000 generation 3 PWR with a reduced power output of around 1000 megawatts. Designed to be more flexible and adaptable to various contexts. And this site fits well also the Italian distribution electricity grid. That is fundamental to consider that. And also, we have a lot of data regarding these kind of reactors. In terms of the methodologies that we adopted, let me go through and guide you. So it's based on 3 main steps. The first one is the setup. The second one is the simulation, and then we have suggestion and recommendation for decision makers. In the initial phase, in the setup, we define the key parameters of the analysis, including the option price, the value of the opportunity to invest in the water basin, exercise price, so the cost required in terms of CO2 to activate the option, so build the reservoir, additional operational costs, so recurring expenses related to reservoir maintenance, as well as preliminary. And we develop a preliminary analysis of the river flow, so assessment of the current and projected water condition to understand the role of the backup basin in enduring a reactor cooling. In the second phase, that is the core of our analysis, we simulated the future river to forecast long-term water availability. We estimated the energy production to assess how the reservoir impact the plant's generating capacity. We calculated the emission saving to quantify the environmental benefits of investing in the basin over the plant life cycle. And then we calculated the NPV to assess the investment profitability using CO2 instead of cash and money as a unit of measurement. We used Monte Carlo simulation, a statistical model technique that used thousands, even millions of random simulations to estimate the behavior of a complex system under uncertainty. It generates a wide range of possible scenarios by varying input parameters according to the predefined probability distribution to obtain a distribution of possible outcomes. This is really flexible and really useful to assess uncertainty. In the last phases, we assess and analyze our results to give recommendation to decision maker building this kind of infrastructure. And we develop a sensitivity analysis to test the robustness of the results against changes in key parameters. And we did the threshold analysis following a paper and the research developed by Professor Locatelli previously to identify the economic and environmental condition under which the investment become worthwhile. So let's go to the key findings. Here in this graph, we present one of the key results, one of the key main simulation outputs. So the distribution on the NPV measured in tons of CO2 saved along the x-axis across 3 different scenarios. So just to give you an idea, the datasets include around 1,000 simulation with data from 2020 and 2018. So you see 3 colored curves the base case in blue show the MPV distribution, assuming that the reservoir is built under an average risk condition, considering rainfall, temperature, electricity demand, and drought timing. And this results is approximately 150,000 tons of CO2 saved in case of exercising the option. The worst case, on the other hand, in purple, where the reservoir is built despite a low drought risk, so the water supply is almost ensured, let me say, and of course it's yield negative MPV in terms of CO2 saving. And the last one in yellow, the best case, assuming that high likelihood of impact of drought risk, and you see is almost beneficial in terms of MPV return. So we also develop a sensitivity analysis, and the goal was to assess how reservoir size affects outcomes under uncertainty regarding water availability and energy demand. So on the epsilon axis, the y-axis, you see the average MPV, and on the x-axis, the reservoir size in terms of equivalent full operational days. And again, you have three curves representing the worst, the best, and the worst, the base, and the best case with the same color legenda. And the areas that you see colored, those are the standard deviation, and the horizontal lines are the MPV. So the optimal sites coming from this analysis of the reservoir to achieve a positive MPV in terms of, again, on CO2 savings is approximately, from our results, 2 days, 2.5 equivalent full operational days. Let me conclude with the key takeaways coming from our research. So we were able to build a real option methodology using CO2 to overcome one of the key limitations of the traditional life cycle assessment that do not consider of the flexibility of the infrastructure where the uncertainty around them. And in terms of option price, we have seen that the basin size has to be around 59 meters and can supply water to 1,000 megawatts nuclear power plant for 12 hours under average weather conditions. So air temperature 25 degrees Celsius and water temperature 15 degrees Celsius. The advantage of this methodology is that it's really flexible and scalable and can be applied to other plants, other technologies. And if you're curious, I invite you to watch also the other videos and to read our papers. It accounts for risk and degrees of freedom, and it also overcomes the limitation of underestimating risk and time scale of electricity production and its impact. And with that, I really thank you for your time in watching this video.